Good everyone. Can you see the screen and hear me? I think the previous screen is still tagged, so remove that screen if you are still seeing the screen of previous presentation, and tag my name so you will see the screen on Bayesian belief network. Okay, so this is seventh lecture, and we are done with naive-based classifier. We will end naive-based classifier today, and we will start with a more general framework called Bayesian network or Bayesian belief network, a bit more complex than what we discussed in naive-based classifier. So what essentially we are doing in this Bayesian probabilistic classifier or probabilistic classifiers of Bayesian family was we were modeling joint probability of features and class. So that is to say probability of x1, x2 up to xn, comma c, where x1 to xn are feature set and c is the class label that we want to predict. And we said there is a probabilistic classifier, so it means that it will look at the example feature values of example, and based on that, it will assign probability to belong to a certain class or probability, different probability for all different class values or class labels. And we did some examples for naive Bayesian case also. But things were easier in case of naive-based classifier because we made a naive assumption, which is also known as independence assumption. We said that x1, x2, xn are independent given the class label. And that's why the joint probability of x comma c, that is probability of x1 to xn comma c, could be calculated as probability x1 given c into x2 given c into xn given c up to xn given c into probability of c. So naive assumption helped us in calculating the probability values easier. So it simplifies our model parameters in terms of machine learning models. But now what we want to do is we want to drop this naive assumption. As many of you have raised in very early first or second lecture of naive-based classifier, like does independent assumption hold everywhere? So I said no, right? That time also we said no. But it simplifies the computation. That's why we started with that. But now let's say what if the naive assumption doesn't hold? So if we drop naive assumption, what happens? Let us see then. So let me draw some cartoon. I will also introduce this notation now. So when we are saying that, let's call this equation 1. If you want to represent this equation 1 as a graph, it would be something like this. So we are introducing some notations here. These notations are called graphical model or graph representation or plate notation also. Popularly, this is also known as something called uh, plate notation or plate diagram. TE or TI, plate diagram. So that is graphical representation of graphical representation of this graphical representation of graphical depiction of conditional dependence. So this is case of naive-based classifier, the red diagram that I have drawn here. So what does it say? It says that this circles represent the circle represents random variables. And this arrow represents dependence. So it says that x1 depends on C, x2 depends on C, and given C, x1 and x2 are independent of each other. So that conditional dependence, independence are modeled through this diagram. So if someone gives us this diagram, we can write equivalent formula that this arrow indicates probability of x1 given C. This indicates probability of x2 given C. This indicates probability of xn given C. And C has no incoming arrow, so it means this is probability of C. A pretty simple thing, but important thing to understand. So please make it clear. And now, what is the equivalent joint probability of this? Multiply everything and you get the joint probability. So that is same as the equation number 1. Are you with me so far? Any question on this? Is the notation clear? Okay, let me give you a small example then. So we are talking about now a joint distribution of 3 variables. So let us say we have 4 random variables A, B, C, D. And I'm asking you to calculate, let me make it a bit more complex. I'm asking you to calculate joint probability of, okay, let me first remove this. I'm asking you to write formula for joint probability of this. Can anyone give me joint formula of joint probability here for this example? So let's try this. So what do we put here? This is A depends on nothing, right? So this is probability of A. C depends on nothing. So this is A depends on nothing. So this is probability of A. C depends on nothing. So this is probability of C. B depends on A, right? So B depends on A. So this is probability of B given A. And D depends on C and B. So this is probability of B given B comma C. So if you want to describe the joint distribution of A, B, C, D, you can write it like this. So this graphical models or these plate notations are a way to describe the conditional dependence and independence between the random variables. Whenever we put an arrow, it means that the uh, variable on the side of arrowhead is dependent on the variable on the other side. So A given B is represented by this kind of arrow. So B given A is represented by this arrow. So in this example, B depends on A, D depends on B and C. And when you don't put arrows, it means that they are conditionally independent. Like in this case, A and C are independent, not conditionally, but they are independent. Uh, does this make sense? Any question on this? Let me add one more arrow and tell me the resulting equation. If we draw something like this, new arrow, new color. What will be the equivalent formula of joint distribution of ABCD now if I put this orange arrow? When we have an orange arrow, probability of A, B, C, D, that is joint probability of ABCD will be what? Can anyone answer this? Only difference, Chintan says replace C with C given A. Great. So only difference is now C is also dependent on A. So the joint model would be something like this. Probability of B given B comma C into probability of B given A into probability of B given B, sorry, into probability of C given A into probability of A. Right? So these graph notations are very easy and simple way to visualize the conditional dependence and independence. Rather than writing the complex equation, many times we can describe things through this simple graph notations. Please take note of everything that I'm writing here because we'll need this eventually in this lecture and in the coming lectures also. So I hope you are taking notes. I will wait for half a minute and please ask me if you have any question on this. Great. So I think it is understood, right? It is understood that what we mean by plate notation or graphical representation of probability dependency. And now we'll see why we need this now. So let us come back to our original idea. We were modeling the joint probability of features and class label, and naive assumption helped us in simplifying the graph or the conditional dependency, and that we could calculate. But now what we are looking for is we want to drop this naive assumption and we want to model. So if there are four variables, probability of let's say three features x1, x2, and x3, and one class, and everything is dependent on everything. We are not making any assumption of conditional independence. Then can anyone tell me how would the graph look like without any dependence assumption? So, or no independence assumption rather. So can anyone tell me how would the graph look like when everything depends on everything? Fully connected, exactly. Maliha says fully connected, perfect. So all nodes are dependent on all other nodes. Something like this. x1, x2, x3, and c. And did I miss any arrow? Yes. So everything is dependent on everything. Still, you need to think about direction, right? Because conditional dependency cannot be cyclic. Still, you need to think about direction. But it means that everything depends on everything. And how do we solve this? Uh, through chain rule, right? Chain rule helps us in solving this. It will be something like this. X1 given everything else into probability of x2 given everything else into probability of x3 given. You need to do it in in like chain rule, and this can be in any order. It is not that you have to first write x1 given x2 x3, then x2 given x3 and so on. You can start with x3 given x1 x2 and so on, but that will decide the direction of this arrow. So if I want to align the arrow direction here as per the chain rule, how would I write? If I want to align with this equation, x1 depends on everything else, so x2 depends on x3 and c. So x2 x3 is given and x2 and c is given. And x3 depends on c. It will be something like this. And x1 depends on x3 also. Right? It will be something like this. If I change the order, then arrow direction would change, but the graph will remain fully connected. Now this thing is very difficult to compute. Because you need to look at all combinations and combination and then you need to figure out. So we don't want this also. We don't want this fully connected network where everything is dependent on everything. But we somehow want to model the dependencies better than what we did in naive-Bayes classifiers. So let's come back to our original example of this COVID-19 example. What we did there was we identified three features, right? X1 was, what was X1? Do you remember that example? X1 was whether the person has symptom or not, whether the person was in contact of someone or not, symptom. X2 was X2 was contact. X3 was whether the person was tested or not. And the class label was whether the person has infection or not. So when we solved it using naive-Bayes classifier, which model we followed? We followed something like this. The C generates X1, X2, and X3. So we said that C generates X1, X2, and X3. But we know that this is not a very good assumption to make, right? Because many times a person is not tested if person is not in contact of anyone or person has no symptom. So can anyone give me a better dependency graph in this example? Try to think of a better dependency and tell me. Yeah, any answers so far? What can be a better dependency model for this? I think, did I lose audio or what? Okay. So yeah, so I was asking a question. What can be a better dependency network for this? Rather than saying that x1, x2, and x3 are independent, uh, given the class, can we say x1 is dependent on x2 or x2 dependent on x3 or x2 depends on x1? Muktan says, okay, contact symptom depends on contact or okay, and there can be other possibility also. Let me try something like this. Let us model something else. How about this? Like if you are, if you have some symptoms, this is what people say, right? If you have some symptoms and if you are in contact with someone, then you should get tested. Whether you get tested or not is conditionally depends on whether you have symptoms or whether you are in contact with someone, right? People do this contact tracing and symptom-based testing and all that. And once you are tested, you need to really see whether you are dependent on or whether you have the actually whether you actually have the infection or not. So that is, or should I change the? I think I should change the direction. So let me do it like this. So whether we have infection or not, it depends on infection generates test. The test generates test is X3, and the X3 generates X1 and X2. So that is the design issue, right? So this is one part of Bayesian network, the designing of a Bayesian network. Devang says X1 or X2. Yes, either X1 or X2 leads to testing. So let's say this is the design of Bayesian network. So one additional task compared to naive-Bayes classifier. In case of naive-Bayes classifier, design of network was always fixed. We said that all features are generated by the class label and features are independent of each other. So we don't need to worry about designing. Now we are talking about design issues, and we are saying that the design is something like this: that C generates X3 and X3 generates C1, X3 generates X1 and X3 generates X2. Or we can have an alternate design of something like this, which we did earlier, like X1 and X2 are the initial features, which generates some feature called C, X3, and then X3 generates C. Now, do you see the difference between these two cartoons? The probability equation would change, right? In both cases, the probability equation would change. What is joint distribution of this one? Let us call this cartoon number 1, and let us call this cartoon number 2. So what is which joint distribution we are talking about when we are drawing cartoon number 1? So when we are drawing 1, in both cases we are modeling this probability of x1, x2, x3, c. But when we are doing it in way of 1, what we are modeling in graph 1? In 1 we are modeling probability of c given x3 into probability of x3 given x1, x2 into probability of x1 into probability of x2. Right, in first case. In second cartoon, what we are modeling? In second cartoon, we are modeling probability of x1 given x3 into probability of x2 given x3 into probability of x3 given c into probability of c. now we are not limiting ourselves to this naive-based graph model where all features are generated from the class label and features are independent given the class label. But now we are deciding what can be the actual dependence between the features. So when we want to model this dependency between the features and class, at that time we need to do something more than the naive-based classifier, and that is Bayesian network. In Bayesian network we do this, and based on the dependency that we have designed. So this dependency graph can also be learned, but that is the more complex part, and we won't discuss it now. But we say that the machine learning engineer designs this dependency graph. So let us say we have chosen the graph number 2. Let's say we choose the graph number 2. And based on that, now we want to solve the problem, or we want to answer our inference questions. So let me remove the first one. Let me rewrite this formula as the probability of x1 given x3 into probability of x2 given x3 into probability of and now, so first thing is to prepare this graph, dependency graph, preparing the Bayesian network. This graph is also known as Bayesian belief network or Bayesian network simply. This is what we call a Bayesian network. And this formula describes the Bayesian network. What next? Now we need to learn this parameter. So this model has how many parameters? How many parameters this model has? Or can you name these parameters? As we discussed earlier, every machine learning model has some parameters to be trained on, or we need to learn the parameter from data. Right? So which parameters defines this Bayesian network? So these are the parameters, right? These are the parameters. When it is Bayesian network, parameters are probability values. So we need to learn these 4 parameters. And how do we learn these 4 parameters? We learn this parameter from data. So let's bring in data here now. So this is the data. What a consistent exponent. Okay. So let me rename this. X1 is symptom, X2 is context. This test. Okay. Okay. So now this is the these are the parameters. This is same as the previous example which we did for naive-based classifier. X1 is contact, X2 is symptom, X3 is test. C is whether the person is infected or not. And we have 10 examples, 1 to 10 samples. So can you tell me what will be the parameter values after training the system with this data? The data that is shown in the table. What we need to do after this is prepare a conditional probability table. That is learning of Bayesian network. So we need to again prepare CPT. And how many probabilities do we want to learn? As we discussed about, there are 4 values, like probability of C, then probability of x1 given x3 and x2 given x3, and probability of x3 given C. Can anyone tell me value of this parameter? of C is simple, right? Probability of C is probability of C to be 0 and to be 1 is given by 8 by 10 and 2 by 10. What is probability table for X3 given C? C can be 1 or 0, X3 can be 1 or 0. So again, count the numbers and tell me what is probability of X3 equal to 1 given C equal to 1? 5 by 8. Okay. Out of 8 cases where C is 1, in 5 cases X3 was 1. Great. Yes. That is 5 by 8. So this should be 3 by 8. And what is probability of X3 equal to 1 given C equal to 0? I think that was 1 by 2, 1 by 2 in both cases. Yes. Similarly for X1, X3 table, what is probability of X1 equal to 1 given X3 equal to 1? So X3 is 1 in 1, 2, 3, 4, 5, 6 cases. And out of those 6 cases, in 3 cases it was 1. So 3 by 6. Yes, great. 3 by 6. And this is also 3 by 6. What is probability of X1 equal to 1 given X3 equal to 0? So X3 was 0 in 4 cases. And out of 4, out of these 4 cases, in all 4 it was 1, right? In all 4 cases X1 was 1. So X3 equal to 1 in 4 cases. We are talking about these cases where X3 was 0. In all 4 cases where X3 was 0, X1 is 1. So it turns out to be 4 by 4. This turns out to be 0 by 0. So what do we do here? We do something called, what do we do when we encounter 0 probability? We add some small fraction, right? So let's say we add everywhere 1 by 2. Just to make sure that the values are not hitting 0. So that is called Laplacian smoothing. And then for X2 given X3. So what are the probability values for this table? Can anyone help me with this? What is probability of X2 equal to 1 given X3 equal to 1? Again it is 3 by 6. And what about probability of X2 equal to 1 given X3 equal to 0? 1, 2. Oh, 1 by 2. So that's 2 by 4. Yes, 2 by 4 and There are 4 cases where x3 was 0. Out of this 4, in 2 cases x2 was 1 and in 2 x2 was 0. Right, so learning remains more or less same as the naive-based classifier, but the probability tables are now different. CPT are now different, and the CPT depends on the graphical model that you have prepared, the dependencies or conditional independence that you have defined. Based on that, your model architecture is different. So this is learning part of a general Bayesian network, and the next thing is inferencing. So again, we can ask inference questions like this. What is probability of C is equal to 1 given x1 is equal to 1, x2 is equal to 1 and x3 equal to 0. Again, we can ask this kind of questions. Now this will be defined by the joint distribution or joint model that we have defined. So what is the model that we had defined? Actually, this given is also not required. We can only say what is probability of this joint distribution. So how do we calculate this joint distribution? This joint distribution is defined by the model that we had prepared, which was this x1 given x3 into x2 given x3 into x3 given c into probability of c. So that is equal to probability of x1 given x3 into probability of x2 given x3 into probability of x3 given c into probability of c. Right. Can anyone quickly tell me the value? What will be the value for this? Now we have CPT, right? From the CPT, we need to directly put the values. So this is 1, right? When I say x1, it actually means x1 is equal to 1, x3 equal to 0, equal to 1, equal to 0, and x3 is equal to 0, given c is equal to 1. This is what I mean, right? So look at this CPT and you get the answer. Maliha says it is 3 by 20. Just verify whether it is correct or not. Are you all getting the same answer? And how do we get this answer? Look at this table where x1 equal to 1 and x3 equal to 0 in x1, x3, 1 and 0. That was 5 by, that was 5 by 6 after normalization. If you want to go without normalization, it is 4 by 4, right? Then the second table was x2 given x3, where x2 is 1 and x3 is 0. So that is 2 by 4. Then x3 given c, where x3 is 0 and c is equal to 1, that is 3 by 8. And c is equal to, c is equal to 1. Why c is equal to 0? 1. And c is equal to 1 is 8 by 10. So does this reduce to 3 by 20? Or? No? Oh, okay. So did I make any mistake here, or where is the difference in the computation? So what is the correct answer or what is the correct computation? And also tell me if I am making any mistake here. Okay, you took 4 by 4. That's fine. That's okay. So that is just to clarify that we need this uh, Laplace smoothing. But yes, 4 by 4 is also okay for this example. Okay, so it will turn out to be something really around 3 by 20. Let's say we'll get something around 3 by 20. Right? But this is how the Bayesian network works. And in addition to the limited capability of naive-Bayes classifier, here we can model the conditional dependency. But that also makes the model complex. And sometimes learning becomes difficult also, and sometimes inference also becomes difficult. So let me give you a more difficult example here. Let us say we want, so let's call this example one. Example one for inferencing. Let me make it more complex. What is probability of C is equal to 1 given x1 equal to 1 and x2 equal to 1? I can ask this question also now. So what is answer here? How do you calculate this value? Or first, can we calculate this value? How do we solve this problem now? X3 is not given, right? So how do we manage X3? With marginalization. Great. Devang and Muktan says marginalization. Yes. So I just wanted to check whether the marginalization is grounded properly or not. So what do we do is equal to sigma for all value of, just I'm adding a new notation, for all value of x3, we want to calculate this. For all, let's say xi. So whatever labels x3 can get, for all label we need to sum it over. So it would be something like this: probability of c is equal to 1, x1 equal to 1, x2 equal to 1, comma x3 equal to 0. Fortunately for us, the example is binary, so there are only two possible values of the x3. Can anyone quickly calculate these two values? So once we have joint distribution of all variable, again we can use the same formula and we can look up in the same table and we can find out the answers. This will turn out to be what? This will be probability of x1 equal to 1 depends on x3 equal to 0. Right? So after marginalization, we need to compute these values. Can anyone tell me the answer here? Is it 1 by 4 or 1 by 4 is summation of both terms? Okay. Can you give me separate answer for both terms? 5 by 40 and okay. 5 by 40 and plus 1 by 8. Just to make sure that all can verify this. So 5 by 40 is also 1 by 8, and so 1 by 8 plus 1 by 8. So both outcomes are equally likely. So that is 1 by 4. So it turns out to be 1 by 4. Are you all getting the same answer? Okay, so then let me make it even more complex. And let's try to answer what is probability of that you are not infected without knowing anything else. Or let to make it less complex, let me add one more example here. Comma x1. Let me add one sample at least. X1 is equal to 0. Let's try this. Akshay is also getting the same answer, but 1 by 4. Fine. How about this now? Yes, Jamin says we are dealing with 4 different cases. Yes, so now we are marginalizing with 2 different variables. So that is x2 and x3 are unknown or are don't care. So we would rather write something like this. This is equal to sigma 4 x2, sigma 4 x3, and then c is equal to 0, x1 is equal to 0, x2 is equal to I, and let's say x2 is equal to j. And I can write something like this. I belongs to. So this is for all I or all labels that x2 can take and all labels that x3 can take. So see, these are binary variables. If they are nominal variables, or if there are 3, 4 cases or possible values for every variable, then you need to sum it over for all cases. So how do we compute now? We have 4 terms now, and that would be is equal to probability of c equal to 0, comma x1 equal to 0, comma x2 equal to 0, comma x3 equal to 0, plus probability of c equal to 0, comma. Yeah. Then it will be something like this. I will leave this computation to you because I want to give you a more complex example. Now, if you notice all the examples that I have chosen were of joint distribution. I conveniently ignored the conditional dependence so far. But can we answer conditional dependence question also? For example, can we answer something like this? So this is beyond this, do it yourself, and I will jump to the next example. There is probability of C equal to 1 given x1 equal to 1 or something like that. This is what we really are looking for, right? If we have some symptom, then whether I'm infected or not. I will be very happy if anyone can give me formulation for this. How do we formulate this thing? Any idea, any suggestions? Okay, let's apply the Bayes rule again. So how do we write this? This is equal to probability of C equal to 1, comma x1 equal to 1 divided by probability of 1 equal to 1. Right? This is Bayes rule, right? This comma means and. So joint probability of C equal to 1 into x equal to 1 is probability of C1 equal to 1 given x1 equal to 1 into probability of x1. So now we need to calculate these two terms. First term and second term. And we have 4 cases for first term and 4 cases for numerator term, equation 1, and 8 cases for the denominator term, equation 2. It will turn out to be something like this. Sigma 4 x2, sigma 4 x3, and then probability of C equal to 1, x1 equal to 1, x2 and x3 for all labels. Divided by, now sigma for 3 things, sigma for x2, sigma for x3. The order of sigma doesn't matter, right? And sigma for C, given probability of anything for C, x1 has to be 1, anything for x2 and anything for. So once you calculate this, it will give you answer the probability of C equal to 1 given x1 equal to 1. And this is what in total, how many terms you need to calculate? 8 plus 4, 12 terms. Let us also write that expansion figure is necessary. Four terms divided by 8 terms. That is probability of and so on. This time you try to complete this, but this is Bayesian network, and in Bayesian network, the complex computation of probability or and inferencing would be more complex than naive-Bayes classifier, and that's why people prefer naive-Bayes classifier because it's pretty simple compared to the computations that we have seen here. We talk more about this next time, and next time we'll also solve doubts. So please bring your doubts. We are done with chapter. Both these are the chapters in your textbook. There is Tom Michel book. So start reading chapter number 1, and I think chapter number 6 for Bayesian network. start reading those chapters. You can also read chapter 2. That is also a useful chapter. So start reading those chapters. Also look at the online material available related to the topics that we have discussed, and we'll discuss doubts next time. If you want to post doubts early, that is better. So you can also post doubts earlier, and we'll continue with this example also next time. Any questions? If there are no other questions, let's end here. Thanks.